Hey everyone. So today we're going to talk a little bit about centripetal force, and what it is, why we need it, and how it's going to help us solve these centripetal force problems, circular motion problems that are going to come. So let's go ahead and take a look. As we talked about last time, um, when we have an object moving in a circle, we need to think about its velocity a little bit differently because it's not moving in a straight line. It's moving kind of around and around and around in a circle over and over again. And so we came up last time with two expressions for the velocity. So velocity is either 2 pi radius divided by the period or 2 pi radius times the frequency. And to remind you, this is the distance you're traveling when you go around the circle once. It's called the circumference. And the period is how long it takes to do that. So that first definition is just distance over time. The second one takes advantage of the fact that period and frequency, how many times you go around the circle each second, are reciprocals of each other. And so it just allows us, if we have different pieces of information, to do different things with them. Now, what we want to talk about today, we've already talked about the velocity of this object. And today I want to talk a little bit about acceleration, which when we studied acceleration before, we studied it as a change in velocity, which is its formal definition. But what we really talked about before was not so much a change in velocity. We talked about a change in speed. So acceleration is a measure of how much things are speeding up or slowing down. But velocity has another component. It isn't just about speed, it's also about direction. And an object that is changing its direction, even if it keeps moving at the same speed, is changing its velocity and is experiencing acceleration. And what leads to acceleration? Forces. So an object that is always changing its direction is always experiencing acceleration and must always be experiencing a force. We're going to use that today as we think about this circle. So let's assume we have this object moving in a circle. We're going to assume it's going clockwise around the circle. So when it's at the top of the circle, for a split second, it's moving to the right. But immediately afterwards, what's going to happen? It's going to change its direction and move down until over here, what direction is its motion in? Downward. And then same thing, it's going to move, change its direction a little, and eventually when it's down here, be moving to the left. And finally, by here, it'll be moving up, and then it will get back to its original place. And it will go ahead and do the whole thing all over again. So what that means is that an object that is moving in a circle is always changing its direction. So it's got to always be experiencing acceleration, and it must always be experiencing some force. And to decide what direction that force is in, we can look at how the direction of motion is changing. So here, if it moves from being to the right, and then next thing we know, it's down, it must have been experiencing some force downward, or else it wouldn't suddenly be moving downward. And similarly, over here, when it's moving down, and then what's next? It's moving suddenly to the left. Well, it must be experiencing some force to the left. All right, two more to go. Moving to the left, but then next thing we know, it's moving upward. Something must be pulling it upward. And finally, upward And then to the right, what's going on? Something's pulling it to the right. So we notice that the force that's acting on the circle is always pulling towards the center of the circle. And we have a special name for this force. We call it the centripetal force. Centripetal comes from words for center, seeking, and that tells us the direction of the force. It's always towards the inside. So, how I think of centripetal force is that when an object is moving in a circle, some force is always changing its direction so that it keeps moving in the circle instead of shooting off in a straight line. And so the force that does that is the centripetal force. Now, something that we're going to see as we go through the rest of this unit is that the centripetal force, that's kind of like an umbrella term. Centripetal. And under that umbrella are a lot of forces that do this. So it might be friction or tension or gravity. But all of them in certain situations are going to be called the centripetal force, the center-seeking force, the force that keeps it moving in a circle. In class, we are going to do a lab on this, and our lab basically is that we have a string that has a mass on the end, and it's connected to a force sensor on the other end. And we spin it in circles, and we decided on three different variables that we were going to look at: mass, velocity, and radius of the circle. So these are things that we thought were going to affect how much force was necessary to keep the object in a circle. Now, when we did this in class, we end up seeing the following three patterns. For mass, we end up getting something linear. For velocity, we end up with something quadratic. And for radius, we end up with something inverse. So let's think about what this means before we try to build this into an equation. First of all, mass. It means that the more mass my object has, the more force I need to keep it moving in the circle. And if you think about this, like swinging a light thing, swinging a heavy thing, oh, the heavy thing is going to be harder. That makes sense. And so increasing the mass increases the centripetal force. Now we see something similar in velocity, but there's a slight change here. When we increase the velocity, we don't just get a linear increase in centripetal force, we get a quadratic increase, which means increasing the velocity a little results in increasing the centripetal force a lot. And then finally, we get one that's a little different. Radius does the opposite. So when we increase the radius, make it a bigger circle, we actually reduce the amount of force necessary. And the way I like to think about that is if I had a car and I needed to turn it in a tight circle, that's going to be really hard. And it's going to take a lot of force in order to do that. But if I'm going to let it turn, but it's going to be in a much wider circle, well, that's a way easier thing for me to do in a car. And it doesn't take as much force. I'm not going to slip or slide. And so it's just easier to do that turning over a bigger distance than over a smaller distance. So we take these three relationships, and we know that for a linear relationship, that means that we could write centripetal force as some number times the mass. We could write centripetal force as some number times velocity squared because it's quadratic. And finally, for our inverse over here, we could write our centripetal force as some number divided by the radius. So, how do we combine all of these into one equation? Well, it turns out if you gather data and look at a huge mass of data, what it ends up working every time is that the centripetal force is equal to mv squared over r. So it's linear with respect to mass, it's quadratic with respect to velocity, and it's inverse with respect to r. Now, I will say when we do this for universal gravitation, because we're going to do a very similar thing with universal gravitation, and when we do this with other situations, a lot of times you still end up with like some constant out here that you have to account for. Centripetal force is kind of cool because it's actually just those three things, and all of the constants, the A's, the B's, the C's, actually multiply to one. And so we end up with centripetal force equaling mv squared over r. Now, tomorrow, we'll do some of our most straightforward questions with centripetal force. But one thing I want us to talk about today is thinking about what doubling or quadrupling or halving each of these variables might do to the centripetal force. So let's go ahead and think about that. If I double the mass of my object, what will happen to the centripetal force? And I'm going to give you four options. Is it going to be 1/4 the original? Is it going to be half the original? Is it going to be double the original? Or is it going to be 4 times the original? You can go ahead and pause the video here in order to um, work through this. There's a couple of ways we can think about this. Um, and so uh, let's think first of all about the pattern. We know that mass has a linear pattern. And so one of the features of the linear pattern is whatever I do this way, an equal amount of it happens this way. So if I'm doubling the mass, then an equal amount is going to happen to the centripetal force. I'm going to double the centripetal force. And that's true. Or maybe we're going to take mv squared over r and think about, well, what happens if instead I have 2m v squared over r? Oh, well, it ends up being 2 times mv squared over r. So doubling the mass basically means that we end up having double the original force. Or both of these are fairly abstract ways of thinking about this. Another thing we could do is what about just picking an original mass, an original velocity, and an original radius. And I'm going to be very easy on myself and say that my mass, velocity, and radius are 1. So my centripetal force would be 1 times 1 squared over 1 for a grand total of 1. And then I could say, okay, what am I going to do? I'm going to double the mass. So now my mass is 2, but my velocity is still 1 and my radius is still 1. And what do I end up with? I end up with a centripetal force of 2 times 1 squared over 1, 2. Oh, it's 2 times my original centripetal force. These are all different ways that you can think about this. Let's go ahead and look at a couple others. What if I double not the mass, but the velocity? Go ahead and pause and think this one through. So what will happen here is a little different because my velocity doesn't look linear, it looks quadratic. And so whatever happens to my velocity, something bigger or more happens to my force. Similarly, if I want to use this way, then I can think about, so mv squared over r is our original. Well, what happens if I have m 2v squared over r? Well, the 2 gets squared just like the velocity gets squared. And so I end up with 4 times mv squared over r, 4 times the original force. And just like before, I could go over here, and if I double, the one that changes is down here. If I double my velocity, my new centripetal force would be 1 times 2 squared over 1, and that is 4. So I would end up with D as my correct answer. It's 4 times the original centripetal force. All right, last one. What if I double the radius? Go ahead and pause. Think about what you think is going to happen. All right, here I end up with this pattern is what I'm looking at. So I know that if I increase my radius, I'm actually going to decrease my centripetal force. So we know that it can't be C or D. It's going to have to be A or B. And so, in fact, over here, what I will see is mv squared over 2r. Well, that is half of the original mv squared over r. And just like before, we can come over here and if we double our radius, what happens? We get 1 times 1 squared divided by 2 is 1/2. So it will be B, half as much as the original. For us, I absolutely expect that you'll be able to do this, and maybe with numbers that aren't 2. Like, what if I tripled it? What if I halved it? Those are all really valuable things to have, and they'll be especially valuable as you move into chemistry and eventually maybe AP Physics. We talk about this all the time. All right. Thank you so much. I will, on our next video, discuss a little bit about tension problems. So looking at those problems where we're swinging an object over our head and solving centripetal force problems with that. Thanks. Bye.